Hello and welcome to the HIV Cure podcast. My name is Sakabo Sisala Marumo and we're bringing you HIV Cure information and the latest stuff in simple language. Today is episode 5 and we're back again. We're talking HIV vaccines, a game changer in HIV prevention and cure. You guys are the best of the best when it comes to breaking down these different topics. And today we're just going to learn about vaccines vaccines are very important when it comes to fighting the different diseases. So I'm going to find out more about HIV and also that the whole science behind HIV vaccines and just a potential to using these to find an HIV cure or to use it in cure strategies. Hi, Dr. Acho.
Hi, Sega. Nice having me.
It's great to have you, finally.
At long last. We've been planning this forever, haven't we?
Yes, but I'm glad it finally happened.
Yeah. We thank God for that. How have you been?
I've been good. I've been surviving. Yes. So today we're talking about HIV vaccines and we just want to know more about you. So kindly introduce yourself and share with us what you do. Yeah.
Yeah, okay. So I'm Acho and for Acho basically, and I'm a medical doctor by training, and I spent the first few years after med school working HIV programs that spans both the clinical part but also public health service delivery for HIV programs. And I got involved in advocacy around HIV vaccines and discussing with the community basically, and persons affected by HIV about what prevention looks like and what a vaccine is and what was in the pipeline around HIV vaccine research. And that's really what got me really more interested in ending this epidemic really, because I think you know this, but I'll take Cameroon where I'm from. There are 500,000 people with HIV, and that gives a prevalence of about 2.7%. And there's a big need, other than the medical part, also the social part. There's a big need for HIV cure and vaccine research to end the health challenges, but also the social challenges that this poses. And that's what pushed me really to want to contribute more. And I'm currently studying a master's in immunology at the University of Oxford. And my goal down the line really is to become active in the HIV vaccine space. My current research group, the research group I am in, is the Rational Vaccine Research Group with Professor Persephone Burrows. And she's an HIV vaccine researcher, and she's also doing a big advocate for HIV vaccine research. And after this, I want to get more involved really in not just advocacy part, but also in the science part for contributing towards HIV vaccine research.
Yes, wow, you do a lot of things. You wear many hats and we love it for you. And also that you're not only in the science part of things, but also in the advocacy, the community, and just making sure that, the voices are heard, and also that you also make sure that you explain to them and they understand better. So I love that. And thank you so much for doing all this work and wearing many different hats, but making sure that you do every one of those roles to your best abilities.
Yeah, I hope I do justice to the explanations, because I feel in the end, all the science without the community being involved is basically useless, right? And also, you can't do science without having the community involved. To do vaccine trials, you need volunteers for the trials. For cure research, you need participants for those trials, and basically we really need everybody involved not just scientists, but also persons living with HIV, persons who are affected by HIV, like the whole world, like everybody really who can participate in us finally ending this epidemic, which we discovered in 1981, but which is still going strong today.
Yes, and we're just going to dive right into it. Can you please explain to us what a vaccine is? How does it help our bodies to fight infections like flu? And also we have like polio vaccines and all these different vaccines that we are young when you go for immunization. And how do they work, these vaccines? And then the most important question is, do we have an HIV vaccine?
All right. That's a good one. I think the more involved you are in vaccine research, the more difficult it is to explain what a vaccine is because it could do so many things. But at the simplest, a vaccine trains the immune system basically to recognize an infection and to fight off an infection. And before we go into it, I'd just like to start by saying our immune system, basically how our system fights off infections, it's really so wonderfully made, and it's really equipped to fight off loads of infections. The reason why most of us are healthy and fine most of the time is because we have very good immune systems. And the immune system, like a muscle, gets better once it has fought off an infection once. So if you think of it, that's why adults don't fall ill as much as children, because they have been exposed to infections before and their immune systems are better. So if you want to help the immune system fight off infections that it hasn't seen better, what you do is you give them something to train with. You give them something that looks like that infection, such that they could train with whatever you give the immune system. It might be a particle of that, a part of that virus. It might be the whole virus, or it might be just something that looks like it, such that the immune system now fights off that infection, develops an immune response, as we would say, against that. And then subsequently, if it is exposed to the real infection a second time, now it is much better trained to rapidly clear the infection and prevent the person or the host from falling sick. So I feel what a vaccine really does is that it helps the immune system to prepare adequately for an infection which it hasn't seen before, such that when it finally sees an infection, it fights it off really quickly. And we've had vaccines for so many diseases before, right? We started off with vaccines for smallpox. We've had vaccines for after that polio. We've had vaccines for diphtheria, and recently we had a vaccine for malaria. And research is ongoing for one day for us to have a vaccine against HIV. For now, we don't have a vaccine against HIV, but there's a lot of research ongoing, such that someday in future we might have a vaccine against HIV. And vaccine research for some diseases is easy. It comes off in a matter of months. Like the COVID vaccine came out in 9 months. But for some diseases, it takes much longer. Vaccine research for malaria started way earlier, like in the 60s, even way before that. And today we just had a vaccine last in 2021. So I think it takes a lot of time for some organisms to be able to be modeled for us to develop vaccines for them, and for other organisms it's a bit much more difficult for us to make vaccines for them, like HIV. So that's kind of why we haven't found a vaccine yet. It might be more complex, but if history is something to go from, if we are able to discover vaccines for others, we might be able to discover vaccines for HIV too in the coming years.
Okay, whoa, that was a mouthful, but beautifully explained. And you also did mention that when it comes to the different diseases, that some it takes a very long time to find a vaccine and all of that. So now the question now becomes that with the HIV vaccine, how is it different to the different vaccines that we know of, such as measles and COVID-19, like you mentioned earlier on?
Okay. Yeah. So maybe we'll take measles, for example, which is a good example, if you started with that. When your body, once your body encounters measles for the first time, it produces such a strong response that if someone has been sick with measles once, they won't get measles the second time, right? So it produces, your body produces a sterilizing immunity after exposure to measles. And that, well, so it means scientists have a model to work from, basically. The body has really, in some people who were exposed to measles, basically, and we were able to claim it and model or build a vaccine from that. But for HIV, for malaria, for example, and many other diseases, we don't have that. So the body does not develop a sterilizing immunity after infection. So there's nothing to build from or to learn from. So that's one reason why, for example, building an HIV vaccine is much more difficult, because we don't have an example to copy from. For other diseases, we have an example to copy from, because the body eliminates it on its own, but for HIV it doesn't. So that's one aspect that's the most obvious one to start from. So there's nothing to copy from. But if we could go further, starting with the virus itself, it's quite difficult to build a vaccine for something that keeps changing. So if you have a target that keeps moving, that keeps changing over time, it's difficult to lock it down. And the HIV virus is very intelligent, because once it infects the host, it keeps on changing, it keeps on mutating, because it replicates in such a manner that the new virions that come out are slightly different from the one that produced them. And that keeps happening over and over and over again, which means that after infection, the person doesn't just have one type of infection in their body, but each one is slightly different from the other. So it's difficult to build a vaccine that will cover all of that. So you might have a vaccine that might cover some strains, but not all strains. So that's also a problem. We need to, because of that variability of HIV. And further than that, there's also the fact that the virus itself kind of subverts the immune system. Like, the virus attacks CD4 T cells, which are really key in building in the immune response. So it kind of kills off who is supposed to kill it. So that's very disappointing. Was supposed to eliminate it. But another point which is really, really important is the fact that the virus does what becomes latent. So once it infects the host, some of the virus incorporates itself into the DNA of some cells, and it basically does nothing. It just goes hiding. It kind of just hibernates, and we call that latency. And this latent virus, which is just hiding in the DNA, in the genome of healthy cells, is called a reservoir. And what this ensures is that you could kill all of the virus which is in circulation, and the sleeper cell viruses which are in the genome will just wake up one day and start replicating again and form more viruses, which is quite intelligent for a virus, but very disappointing for vaccine researchers and cure researchers too. And on, but there are so many reasons which stem from the fact that the virus keeps changing. 2, the virus hides and incorporates itself into the host. 3, there's no model to copy from. Even in animals, there's no HIV model to copy from. And this also leads to the fact that it's difficult to study the virus, because you can't have a good animal model of the virus to build a vaccine in. So all these factors make it such that it is much more difficult to make a vaccine for HIV than other infections, which we are much more familiar with and which we have built vaccines for.
Okay, so clearly this virus, the HIV virus, is very smart and it's changing and all of these things, but we know that we have smart scientists and researchers like you, Dr. Acho, who are working very hard when it comes to immunology and making sure that when it comes to and just making sure that we have different ways of how we can counteract these different diseases. We have the options. And now, what's the difference between a preventive HIV vaccine and a therapeutic one?
Yeah. Yeah, I would also start by saying we also have very powerful advocates like you who keep everything going together, right? Yeah. Regarding the question you asked about, most of us are familiar with the term preventive vaccines, basically. And when we are talking in the classical sense that when we're talking about vaccines, we are talking in fact about preventive vaccines, which are um, s- what we take to prevent us from a subsequent infection. So when children are born, we give them vaccines to prevent them from getting infections later on in life. So those are preventive vaccines, basically. Preventive vaccine like a seatbelt. When you get into a car, you buckle up your seatbelt so that if you ever have an accident, you won't be severe, right? So you take it before the infection ever happens. But therapeutic vaccines, you rather give them to people who already have the infection. And the goal of a therapeutic vaccine is to guide the immune system to more effectively eliminate the virus which is infecting it. So, um, you basically one is there to prepare you for an infection which hasn't happened yet, and which eventually might not even happen. And two, the therapeutic vaccine is more in the case where you have someone has an infection already, but the immune system isn't dealing with it yet or dealing with it adequately. So you want to train the immune system to, and one might think of it but if you think about it well, you realize there's a big use case for each one. Currently, there are 38 million, 39 million people living with HIV. And if we could have a vaccine that could train the immune system to clear the infection in those people, then it will be wonderful because in the end we will have no HIV again, since HIV is spread from human to human, right? So it's a human virus. So that's the key, that's a wonderful use case for a therapeutic vaccine. But why waiting for that even? A preventive vaccine will prevent 8 billion people from getting newly infected, basically, because each year there are about 1.3 new infections every year. And if we can prevent those 1.2 million infections every year by protecting everybody who is not yet affected, it means we could prevent subsequent infections and we could end up controlling the epidemic. So there's a use case for each one, and the public health arsenal needs both for us to be able to create a world which is HIV free, basically. So that's the simple way of viewing preventive vaccine and therapeutic vaccine and understanding the use case for each one.
I know that earlier on you did mention why we don't have an HIV vaccine now, like some of those challenges that are there. But I know that a lot of my listeners are just waiting for this question. So I'm going to ask it again that COVID-19, like you did say, it just hit in 2020, and then 2021, we have different vaccines that are available for us to take, and not just one, but different options, we had like Pfizer, different options when it comes to COVID vaccines. So why don't we have an HIV vaccine, even though we've had HIV for the longest time, for over 40 years around, and we've had people doing researches over the years?
Oh, wow, wow, wow. Yeah, I think this question keeps coming back. And I think before we start,
Mm-hmm.
let us admit also that the COVID vaccine builds on decades of science. Like coronaviruses have been known forever. It's just that this was a new strain that emerged and was really, really tough and was really, really infectious and had great morbidity. And that's why SARS-CoV-2 came about. But the coronaviruses have been known, and scientists have been working on them for a while, right? So they understood the virus quite well, and they were able to build on what they already knew to be able to produce a vaccine. And that was a miracle because it changed it stopped us from lockdowns and mask mandates and all that. So that I just wanted to put that out there before we go further. So, and also just add the fact that the COVID virus is also quite simple. Is much simpler than the HIV vaccine, and it's much more stable. It doesn't evolve as much, so it was also easier to build a vaccine for that. So I just want to put that out there. And now regarding the question of why HIV is much more difficult for vaccine development. And I think I'll just summarize what we said earlier again. I think the first part is there's no model for it. There's nobody. We had people who spontaneously cleared COVID, for example, and that was most people even. Most people spontaneously cleared COVID. HIV, once you're infected, you're infected, right? You spontaneously cleared. The immune system becomes activated and produces antibodies, a lot of antibodies, but none of those antibodies that can clear the infection. There's none of those antibodies that can control the infection. And those really participate in exhausting the immune system even. The immune system gets so much activated that it becomes exhausted and can't fight off the infection adequately. So that's another problem again. So in as much as it goes further and confuses the immune system, it wipes off CD4 cells, and it does all of that. So these are all factors which come into place to make it realize again that the virus is much cleverer than we think, other than the points we mentioned about the virus becoming latent and and all that. So those are some elements we should think about. And I don't know. I think I don't have anything else to really add to why we haven't found a vaccine yet, which is not a lack of effort, but I just feel it's a much more difficult virus to work with. And yeah, and hopefully with the much more brilliant scientists who are in the labs and who are coming up, hopefully we will be able to find answers to this. And someone might listen to this 10 years ago and be asking themselves why we were stuck for so long. We hope that's the case. Yeah. But I just feel it's much more difficult to work with, basically.
Okay. And then earlier on, you also mentioned that when it comes to our bodies, they're very smart when it comes to fighting infections, and that the vaccines help. So what does the immune system need for HIV? And then how can then a vaccine help with all of that, with fighting off HIV?
Oh, okay. So in an ideal world, the immune system will be able to recognize one part of the HIV virus, right? And form strong, powerful antibodies, potent antibodies against that, which will bind virus each time the virus is seen, and will draw immune cells to clear up the virus, or which will bind on cells that are infected and will draw immune cells to clear up those cells, and the body will basically wipe off the infection. So in our ideal situation, that's what we want to see. But as of now, we don't have that basically. So if we were able to, what help, if I got a question, help clearly, what help the immune system would need to clear up the infection, it will be adequately and specifically and very potently recognizing the virus and infected cells, and then two, mobilizing immune cells, be they T cells or macrophages, basically pulling cells in to kill off those infected cells and to clear off the viruses such that infection is cleared. So that's what the immune system needs in an ideal world, but we don't have that yet. So we need to be able to, one, probably use a composite of all of those, train the B cells to produce antibodies that can potently bind infected cells, train T cells to be able to identify infected cells, train NK cells to find infected cells and clear them basically, and also find cells in them but are not actively replicating, basically find cells that have latent virus in them and be able to clear them also, so that there will be no reservoir left. If we're able to do all of those things, I think train the immune system to do all of these things, then we'll probably, that's an ideal case. or a vaccine, and a vaccine that can do all of those things will be a good vaccine for clearing HIV. I don't know if I think if that was the question, then that's probably what the immune system wants to see to be able to fight off an infection. Yeah.
Okay, no, thank you for that explanation. And then now that we know the role of the immune system, we want to know now what scientists are currently doing, that when it comes to testing for HIV vaccine research, what's currently happening in labs around the world, or maybe even what you are working on.
Yeah. So, I have no work. So my research work actually, despite being working for a PI who is actively working on HIV vaccines, my work is not on HIV vaccines, rather unfortunately, but at least I get to learn from her work. And so she's a really brilliant lady, and she's working around understanding. She's really more understanding the mechanics in priming B cells to produce broadly neutralizing antibodies. And for example, understanding how glycans on the HIV envelope influence antibody responses to that basically. But since I'll give a bigger picture of what HIV vaccine research looks like, and just to say we're in the time where momentum is kind of building, because it had waned at one moment. In the late 1998, 1999, 2000, that's when there were there was a lot of momentum to build vaccines for HIV. And the way they did it was the way they had done vaccines for other viruses, where they took parts of the virus and they wanted to make responses against those parts of the virus, basically, right? So maybe they take GP120, which is the part of the virus, and then they try to make to expose and see if they can produce responses against those, and if those responses will prevent infection. And that's how vaccines were made for many viruses. Take smallpox, take all of those viruses. But that didn't work for HIV, and they did that for a number of trials, and it didn't work. And that's when they quickly realized that HIV might be different. So the classical pathway of vaccine development has shown little or modest responses. But the second thing scientists have observed is that in persons who have HIV and have had HIV for a while, the B cells are basically what produce antibodies, basically. And after repeated exposure to HIV, they start producing antibodies that can protect against a large number of strains of HIV. Because as we mentioned earlier, HIV is very diverse and it has so many strains. So they start producing antibodies, but multiple strains of HIV. And they don't just do that at a moderate level. They do it very potently. And so they call those broadly neutralizing antibodies, because those antibodies neutralize multiple strains of HIV and they neutralize them potently. So that's what they observed. And having observed that, they started studying how to produce these broadly neutralizing antibodies. And it has been really tough, because these broadly neutralizing antibodies are produced after the immune system is exposed to HIV several times. So producing that in a vaccine is a bit difficult. So what researchers are trying to do now is to be able to identify potential B cell precursors, like early B cells, young B cells, which they think would one day produce, if they mature them enough, can produce these broadly and potently neutralizing antibodies, right? And so what they are trying to do now is be able to identify this type of cells, develop vaccines that can guide this type of B cells along that journey to produce these potent broadly neutralizing antibodies in a very short time, not after years of infection, but maybe after you vaccinate once with this immunogen and vaccinate twice and thrice, and after 3 or 4 sequential vaccinations, you might have identified and guided these B cells to grow and produce the antibodies you want. So it's kind of like taking a child from primary school, you're teaching them something else, secondary school, you're teaching them something else, university, you're teaching them something else, so that they become very good at producing what you want, right? So that to produce those broadly neutralizing antibodies. So that's one strategy that is being used. And if that comes to fruition, it will have a lot of potential, because it will not only help in prevention, because that it will help you to produce antibodies that can do prevention, but it can help use a therapeutic vaccine, right? Because people who have HIV could be vaccinated in that way, and then they will be able to neutralize the viruses they have. So that's also a therapeutic. So you have applications in both ways, and even beyond that, you could have prevention from mother to child transmission and all those type of cases. So that is really potent and wonderful emerging field of research. And I'm sure you've heard a lot about these broad interest antibodies, and as an advocate, you have a lot to say about them. So that's one area of research which is really exciting. But other than that, what one other interesting method of research is the idea that given that the virus keeps mutating, what if we stop targeting the parts of the virus that are mutating a lot, right? In this case, we're not trying to produce broadly neutralizing antibodies, but we're trying to produce T cells that can specifically target the parts of the virus that the virus absolutely needs to survive. So they call those highly conserved areas of the virus, because irrespective of how much it changed, there are segments of the virus that they don't change because they absolutely need it. So some researchers are also trying to build viruses against those specific parts of the virus that are highly conserved. And though this has not met as much success, if we can if this is possible, if this eventually produces great results, it will have a lot of potential, right? Because in that case, we'll have just those antibodies, those T cells. If you can produce vaccines that elicitate those T cells, then they'll be able to treat or prevent the infection, no matter how varied or how the virus mutates again. So that's also one very cool side of research. And I'm the only one fascinated by this listed option. That there's this group who found a group of who basically developed some epitope, some vaccine against a form of HIV that infects more of primates. So they call it the simian immunodeficiency virus, SIV. And they used a vector. Basically, they put the immunogen in a CMV, which is cytomegalovirus vector, and then they introduced this into some primates. And what they observed is that all those primates initially developed, and then they later exposed, so they produced the vaccine using the CMV vector, and then they exposed those primates to it. And then later now they challenged those primates with the simian, with the CIV virus, basically. And what they initially observed is that all the apes, all the primates got infected. But later on, 50% of those primates cleared infection and were one. Yeah, so as I was saying, that it's so interesting because they were basically able to produce a vaccine that was 50% efficacy, with 50% efficacy in non-human primates, which is wonderful, basically. And the sad part about it is that they have not been able to make a jump from those results from primates to humans. They have not been able to translate that into humans. I don't know. It could be basically that it's just that specific for the C virus. It could be that they have not just been able to translate it well for humans. But I'm just excited by seeing that, because I think that's the highest level of efficacy for a vaccine that is specifically targeting T cell responses that there is out there. And if they could translate that from what they are doing in primates to humans, then it will be spectacular, really. And then there's the new things that are coming up now with the emergence of mRNA technology. It becomes a lot faster now to do research in vaccine development. Basically, you can develop a vaccine in a matter of days or weeks. So it's a lot easier now to do vaccine research. So I think we now have the tools to be able to do to advance some of the really interesting research that is possible. And that's why it's really an exciting time to do vaccine research.
All right. And I know that, my listeners are like, whoa, well, the primates, options and everything, like you really got us enticed. So don't worry, we will learn more when it comes to HIV vaccines and the options. And you also did talk about BNAbs, the broadly neutralizing antibodies. And to our listeners who might have say, okay, I want to learn more about that, or what exactly is beyond what Acho explained. So be on the lookout for our next episode where we are going to look more into BNABs and just learn more on how they work and how they might be a game changer from, just from Acho's excitement on the options or yes, the various options of vaccines that could actually work. And you also did, we talked about, you talked about how the mRNA, the different options that are there. So it means that a lot of scientists across the world are working on the different options that are there. And also now we want to know that when it comes to HIV vaccines or just generally vaccines, why are they important when it comes to ending HIV globally? Why is an HIV vaccine a very important tool for us to end HIV globally?
Yeah. The flu vaccines are really a game changer because, as I mentioned before coming to this, I was working in HIV service delivery, and just the logistics around ensuring that health facilities have drugs to give for persons living with HIV, just the logistics of sorting out PrEP that you can procure PrEP drugs, and then you can effectively give it to all those at risk for HIV, so that they can take it and are not at risk. Just the logistics around managing pregnant women living with HIV, so to prevent transmission from. I feel we've gone a long way with biomedical interventions for prevention and treatment, but it's really challenging, right? It's so challenging. I've not worked on the cost side, but I can imagine buying and distributing this is also a lot of investment financially, and it needs, so for some mind, it's really just so costly, really. And now we look at the human perspective, um, the adherence challenges of first for drug therapies, the risk of resistance after years on treatment, and all of those things. It really means that um, our progress towards with biomedical research, with drugs, was should be viewed more like a stopgap strategy to prevent further infections, to prevent further mortality. But ultimately, we need to find a cure for people with find a therapeutic vaccine for people with HIV. We need to find a vaccine to prevent new infections, basically. I think that's the ultimate thing we need to ensure an AIDS-free generation. I think I like using that sentence because that was one of the mottos of Elizabeth Glaser Pediatric AIDS Foundation, where I worked for a good number of years, and where my heart always is. So basically, we really need a vaccine to ensure an AIDS-free generation. And the reason for that is really that it is cheap. Once someone is vaccinated, essentially we might need booster doses, but essentially we've protected that person from infection subsequently. If we find a therapeutic vaccine that can cure an infection, then effectively we have stopped that. The person no longer needs to take treatment every day. The person is no longer resistant. So it really saves a lot of that. And beyond the hard facts and all the statistics, it's also about the person, right? It will essentially mean that more mothers could give birth to children without any risk of fear of transmission. It essentially means that persons living with HIV, they get a therapeutic cure, who wouldn't have to bother about the stigma associated with that, wouldn't have bother about taking pills every day. So I feel there's a human side to it, which is very powerful, why we need these. There's also a public health part of it, which is very why we need this. There's an economic side to it. So I feel all the reasons are there. It's just the science that is limiting us now. We don't have enough scientific capacity right now, and doesn't permit us to respond to all these needs. But the case for a vaccine is really, really strong. Even with the emergence of long-acting PrEP, which we probably need once a year or twice a year, even with the emergence of that, a vaccine is still a more beautiful alternative because it's still you take it for a short period, you take it once, or you take a few doses, and it's sufficient for a lifetime. or is sufficient for a long time. We don't know how, maybe 15, 20, 30 years, but a vaccine really covers a much longer time than long-acting PrEP will do. So, or long-acting therapy will do. So even with these advances in medical and in treatment and in prevention, which uses medications, a vaccine or an immune therapy really is still a much more beautiful alternative than them.